Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Fluid transport in pipes. Piping system design considerations part 1, line sizing. In this video course, you will learn the factors to be considered in piping system design, concept of economic diameter of a pipe, guidelines, equations and steps involved in the sizing, a case study in line sizing. Please subscribe to the channel. By subscribing, you will motivate us to produce knowledgeable video content for you. So please subscribe now before you forget. Piping is an important element of fluid transport processes. Fluids are transported from one point of location of the process activity to another location through piping system. A typical piping system consists of various types of fittings such as T's, elbows, valves, expanders, reducers, gaskets, drains, vent, etc. Shown in this figure is a fractionation tower which consists of several process equipment interconnected by piping system. Some pipelines consist of only few fittings such as flanges and no valves, while others have many fittings, valves, expanders and reducers, etc. These pipes vary in size depending on the nature and quantity of fluid transported. This figure shows a storage tank facility in a refinery which receives or delivers oil and oil-related petroproducts through pipelines made of steel over long distances running into several hundred meters. These are cross-country pipelines with several individual pipes connected by flanges or welding. Note, there are essentially no valves in these pipelines. Valves are provided only in the delivery tank terminal and the receiving storage tank. Design of piping systems such as this should take into consideration several factors. The most important of them is the safety of the proposed piping system. Piping system presents the largest risk to the plant safety due to presence of large number of joints in the piping network laid out over the entire plant. Piping system design consists of three important activities: selection of piping materials, hydraulic design of piping system, selection of the type of valves. Piping system design, selection of pipe materials. Factors to be considered in piping material selection. While selecting materials for piping systems, the factors to be considered are compatibility with process fluids handled, maximum and minimum working temperature and pressure, possibility of exposure to the fire hazard, susceptibility of the pipe and joints to corrosion, refrigeration effect due to sudden expansion or loss of pressure with volatile fluids, that is refrigerant flow, cost and availability. This table shows typical metals and non-metals used for piping system. Among the metals, cast iron, high silica iron, carbon steel, high alloy steel, nickel and nickel-based alloys, titanium and titanium alloys are commonly used. Among non-metals, thermoplastics, thermosetting resins, borosilicate glass and graphite are widely used. Material selection is an optimization process. The material selected for an application is the one that best suits the given applications, meeting the above-mentioned factors. Pipe sizing, the economic diameter concept. Pipe sizing is an important design activity of a process engineer. What do you mean by pipe sizing? Pipe or line sizing is to determine the diameter of the pipe for a given fluid transport duty. What should be the size of the pipe for a given flow? Theoretically speaking, the optimum pipe diameter is the one that gives a minimum total cost of the piping system. That includes the operating cost and the fixed charges, that is the cost of piping, of the system. The operating cost is the cost of pumping or blowing power consumed to deliver or transport the fluid through the piping system, overcoming the pressure drop. Larger diameter pipe will result in lower velocities and hence lower pumping or blowing or compression cost. This figure illustrates the relationship between the pipe diameter and the total cost of ownership, which is the sum of the annual fixed charges, that is the cost of piping, and the cost of pumping. As the pipe diameter increases, the pumping cost decreases, but the fixed charges increases. The optimum diameter is where the total cost of ownership is minimum, as indicated by the point O in the figure. Having understood that one needs the annual cost of piping, that is fixed charges, and the annual cost of pumping or compressing to determine the optimum diameter of the fluid flow, let us now move on to find out how to estimate the cost of piping and the cost of pumping or compressing. We will focus our attention on estimating the line size of a liquid flow through a piping system. Similar approach can be used for sizing the lines for gases also. Line sizing for liquid flow. Guidelines for cost of piping and engineering equations for pressure drop. The cost of piping is a function of the diameter and it increases with increasing diameter. For ordinary steel pipe up to nominal size 1 inch, the cost of pipe C pipe varies directly with pipe diameter D. For larger pipe sizes, the cost of pipe varies directly with diameter to the power 1.5. In general, for the estimation of annual cost of piping of any diameter, the annual cost per unit pipe length is taken, which is expressed as C pipe equal to K times D to the power N, where K is the proportionality constant, N is the constant which depends on the pipe diameter. The cost of pumping is simply the work done by the pump in overcoming the pressure drop or head loss in the system. Work done equal to pressure drop times the flow rate. By determining the pressure drop in the piping system, the cost of pumping can be evaluated. The flow of liquid through a pipe is resisted by viscous shear stresses within the liquid and the turbulence that occurs along the internal walls of the pipe, created by the roughness of the pipe material. This resistance is usually known as pipe friction. It is measured in feet or meters head of liquid. Thus, the term head loss is also used to express the resistance to flow. From the energy point of view, the head loss or pressure loss is the energy used to overcome the resistance to flow. This results in gradual decrease of the pressure of the fluid falling from one point to another in the direction of flow of the fluid. Illustrated in this figure is a liquid flowing from a tank through a pipe and discharging into open area. Due to resistance to flow, head loss occurs in the pipe as a liquid flow from point 1 to point 2. If pressures measured at point 1 and point 2 are P1 and P2 respectively, the difference between the two pressures P1 minus P2 is called the pressure drop. Many factors affect the head loss in pipes that include viscosity of the fluid, the size of the pipe, the length of the pipe, the roughness of the internal surface of the pipe, the changes in elevation within the system. The resistance through various valves and fittings will also contribute to the overall head loss. In a well-designed system, the resistance through the valves and fittings will be of minor significance to the overall head loss. Head loss is determined from Dorsey-Weisbach equation as expressed below. HF equal to FD times L by D times U squared by 2G. Head loss can also be determined using fanning friction factor, which is expressed below. HF equal to 4 times FF times L by D times U squared by 2G. Where HF is a head loss, F is a friction factor, L is the length of the pipe work, D is the inner diameter of the pipe work, U is the velocity of the fluid, G is the acceleration due to gravity, FD is a Dorsey friction factor, FF is a fanning friction factor. As mentioned in the above equations, two variants of the friction factor are in common use. The fanning friction factor FF equals 1/4 of the Dorsey friction factor. The Dorsey friction factor, which is 4 times greater than the fanning friction factor used with Weisbach equation, has now become the standard head loss equation for calculating the head loss in pipes where the flow is turbulent. The friction factor can be estimated from the Colebrook-White equation for fluid flow for RE greater than 4000. 1 by square root of F equal to 1.14 minus 2 log to the base 10 times E by D plus 9.35 divided by RE times square root of F, where F is a fanning friction factor, E is the internal surface roughness, D is the inner diameter of the pipe work. In meter, RE is a Reynolds number. Friction factor F is present in the equation on both sides. This equation should be solved by trial and error method. Moody's chart plotted from Colebrook equation provides accurate estimation of friction factor. This chart, also known as friction factor chart, is a plot of RE versus friction factor for different pipe relative roughness E by D. Line sizing, the steps involved. In process design, the nature of the fluid flow rate, and other operating parameters such as fluid temperatures are known. You are required to find the size of the pipe for the given flow rate. The flow rate is what is taken from the process design document, process flow diagram of that section of the plant. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. The steps involved are: take the flow rate Q from the relevant process drawing PFD. Estimate the length L from the process equipment layout. Select the pipe material compatible with the nature of the fluid handled, considering the cost, etc. When these three input data are decided, we are left with two unspecified parameters. One, the head loss HF or the pressure drop delta P. Two, the diameter D of the pipe. If one of these two parameters is fixed, the other one can be calculated. In process design, usually the line pressure drop is specified. It is general engineering practice to specify the pressure drop per unit length, that is, delta P per meter of pipe. Line sizing, a case study. We will now walk you through a case study in which you will learn how to size a pipeline. Problem statement. Water from an atmospheric tank shown in the figure is pumped to an open discharge area through a pipe of diameter D made of carbon steel. The flow is regulated through a globe valve to maintain a discharge rate of 225 cubic meter per hour as shown in the figure. The elevation of the discharge end of the delivery pipe is 4 meters from the pump suction line. Take viscosity of water as 1 cp. The pressure drop in the piping system shall not exceed 2 psi per 100 feet, that is 46.12 mm of water column per meter. Calculate the diameter D of the pipe. This figure shows the piping system details for the line sizing problem. The data given are fluid pumped water, flow rate 225 cubic meter per hour, the viscosity mu equal to 1 cp, material of pipe carbon steel, pressure drop not to exceed 2 psi per 100 feet of pipe. The length of the pipe from the layout is L equal to 20 plus 4 plus 100 equal to 124 meter. In this sizing problem, the pressure drop in the system is specified and you are asked to determine the pipe diameter D. The pressure drop is nothing but the friction resistance HF in the piping. In the design problem, a pump is used to develop a head to overcome the frictional resistance. Hence, it is reasonable to assume that the pump differential head is equal to HF. Given that the pressure drop not to exceed 2 psi by 100 feet, that is equal to 46.12 mm water per meter of pipe. The total length of the pipe L is equal to 124 meter. So the HF equal to 46.12 times 124 to 5.72 meter. Q equal to 225 cubic meter per hour, which works out to 0.0625 cubic meter per second. U equal to Q by A equal to 4 times 0.0625 divided by pi times D squared, which works out to 0.08 D to the power minus 2. Head loss is determined using fanning friction factor is expressed below. HF equal to 4 times FF times L by D times U squared by 2G. Substituting the values of L, U and HF, we get the value of fanning friction factor FF in terms of D. FF equal to 35.53 times D to the power 5. Similarly, determine Re equal to du rho by mu in terms of diameter d. Re equal to 80,000 times d to the power minus 1. Since the fluid is water, we can assume the flow to be turbulent. For turbulent flow, the friction factor can be estimated from the Colebrook weight equation with NRE greater than 4000. 1 by square root of F equal to 1.14 minus 2 log to the power 10 times E by D plus 9.35 divided by RE times square root of F. Substituting the previously obtained values of friction factor F, Reynolds number in terms of D, and taking the surface roughness E equal to 0.00005 meter, the Colebrook weight equation becomes 1 by square root of 35.53 times d to the power 5 equal to 1.14 minus 2 log to the base 10 times 0.00005 divided by d plus 9.35 divided by 80,000 times d to the power minus 1 times square root of 35.53 times d to the power 5. The left hand side and the right hand side of the equation are in terms of the variable d. Solving for d, we get d equal to 0.21 meter, which is equal to 8 inches. The nearest available commercial pipe size is 200 mm. Hence, select pipe diameter of 200 mm or 8 inches. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.